Hi everyone, my name is Florian, and in this video I'll present our work on adaptive attacks to adversarial example defenses. This is joint work with Nicholas Kalini, Valen Brandl, and Alexander Madry. So this talk is about adversarial examples, this curious phenomenon in machine learning models where very small changes to an input can cause a complete change in a model's prediction. So here, this image on the left that's correctly classified gets slightly perturbed, and now the model thinks it's looking at a picture of guacamole. So why should we care about adversarial examples? I think there's two main complementary reasons to study them. The first is because they give a lot of control to adversaries against deployed machine learning systems. And this has strong implications for the use of machine learning in computer security for things like malware detection, or web security, things like detecting ads, phishing campaigns, or forbidden content. And on top of this, studying adversarial examples might also help us understand models' robustness to distributional shift in a more general sense, with the ultimate goal of building more reliable and safer machine learning models. And building models that are robust to adversarial examples is a very challenging problem, and many people have tried to solve it. Actually, the number of papers on this topic has really exploded over the past 2 years, and on average, I'd say there's probably one new defense paper published on arXiv every day at this point. But the field is being held back by a difficulty to properly evaluate these defenses. So in this work, we reviewed 13 peer-reviewed defenses that appeared at one of the leading machine learning conferences over the past 2 years. And all these papers propose some interesting new way of defending against adversarial examples, and they all evaluate their proposed defense quite thoroughly, usually by following some well-accepted guidelines and standards. And yet we find that for every single one of these defenses, the actual robustness was overclaimed. And with a suitably designed attack, we can reduce the defense's accuracy significantly, typically to 0% accuracy within the threat model that the authors originally considered. So if you've been following this space over the past years, this might not really come as a surprise. And our paper isn't the first one to reevaluate a bunch of defenses and to show that they're broken. Actually, my co-author Nicholas has been doing this for the past 3 years now. But when we initially started this project, we were expecting quite a different outcome. Actually, our initial goal was to show that evaluations of defenses against adversarial examples are improving. And the reason we were optimistic about this was that the field has slowly come to a consensus on what constitutes a good evaluation. So first, we've mostly converged on some simple and clearly defined threat models where the adversary gets full access to the defense parameters. We call this a white box attack. And the adversary is just constrained to producing perturbations that are small under some fixed norm. Now, of course, a lot has been said about this type of threat model and how this norm constraint is somewhat arbitrary and unrealistic, but at least this gives us a surprisingly hard but well-defined problem to study. The second important change in the field has been about recognizing the importance of so-called adaptive attacks that are specifically tailored to break the defense. And this may seem obvious to people in the security community, but actually in this space, a lot of evaluations of defenses have in the past been just about showing that previous attacks don't work, rather than really trying to break the specifics of the newly proposed defense. And we did really find that the evaluation standards do seem to be improving. So over the years, we find that authors, and probably reviewers too, have recognized the importance of evaluations against adaptive white box attacks. And among the 13 papers that we reviewed in our work, 9 of them explicitly aimed to create an adaptive attack that was tailored to the defense that they proposed. And another very nice change that we've noticed in the field is that nowadays pretty much every defense comes with a public code base, and often even with pre-trained models. And this also wasn't the case 2-3 years ago, and this makes it much easier to allow for these independent reevaluations of defenses. So if evaluation standards have indeed improved, then why were all these defenses still broken? And the answer is quite simple. We find that while many evaluations did try to include adaptive attacks, they basically failed to design a particularly strong attack. And the authors then take the failure of these attempted adaptive attacks as a sign of robustness, even though better designed attacks would have actually been much stronger and broken the defense. And so this is where our work specifically comes in. For each of the 13 defenses that we considered, we were able to come up with a much stronger attack than one originally considered in the author's evaluation. And rather than just showing this final attack, we actually wrote down our entire process for coming up with it. So usually this started with reading the paper and finding something strange or missing in the original evaluation. Then often looking at the author's code also helped in confirming some hypothesis about why the originally considered attacks failed. And we really didn't try to cherry pick which results to present. So for some defenses, we thought up some adaptive attacks, tried it, and it worked. In other cases, it didn't, so we wrote this down and tried again until we found the final attack that worked. And all of this is in our paper as a kind of case study or tutorial for how to build stronger adaptive attacks. So for the rest of this talk, I'll go over some high-level lessons and observations we've made from evaluating these defenses. And these will be formulated mostly as things one shouldn't do when building or evaluating a defense. And if you're interested in the more nitty-gritty details of our attacks, please take a look at the individual case studies in our paper. So one of the first things we noticed, and we're actually quite surprised by this, is that there are a bunch of recent defenses that explicitly aim to break a model's gradients in order to break gradient-based attacks. And this is unfortunately just the wrong way to think about this problem. And that by messing up gradients, we're most likely going to cause many existing attacks to fail, but that shouldn't be the end goal. The model hasn't been made more robust, and we found that these types of defenses are usually just very easy to defeat with some form of gradient-free attack. And this really goes to the heart of what a good adaptive evaluation should do. An evaluation shouldn't show that the defense resists some specific attacks, but it should make a convincing case that it can resist all attack techniques in some attack model. And so this approach of trying to obfuscate gradients is just not going to be able to achieve this. And this brings us to our second observation about the reuse of adaptive attacks from prior work. So what many evaluations will do is that they'll take a successful adaptive attack that worked on a prior defense and repurpose it somehow against a new defense. And two very popular victims of this approach are the BPDA and EOT attack strategies that were introduced by Italia, Carlini, and Wagner. So if you're not familiar with these are somewhat generic attack techniques to approximate the model's gradients when the model is either non-differentiable or somehow randomized. And these techniques have been used successfully against many defenses in the past. But this does not mean that they're always appropriate to use. So we should really take the time to understand why previous adaptive attacks worked before using similar ideas in a new evaluation. Because these prior attacks were specifically tailored to some defense, we have to make sure that the same assumptions and invariances hold for the new defense we're trying to evaluate as well. And that's why our paper gives a lot of details on our process for designing each attack, because usually there's a lot of assumptions that have to be met for each of these attacks to work. And some specific advice I can give on these particular two techniques. I try to use BPDA mostly as a last resort. It's a relatively blunt hammer kind of tool that is great when it works, but more often than not, gradient-free attacks will just do better. And as for randomized defenses, I find that it's usually easier to first try to build an attack that works when the randomness is fixed. And then once you've found an attack that works in that setting, to try to average over the actual randomness of the defense. So another pattern we noticed in many defense evaluations is just a lot of unneeded complexity. And one reason is that defenses themselves have gotten exceedingly complex. And for some reason, this seems to be particularly true of defenses submitted to security conferences. So as a generic example, it's not uncommon to see defenses that look a bit like this. First, you have some kind of pre-processing that's often randomized. Then you have many different components, often different neural networks that jointly reach a prediction. And then on top of that, you'll have some kind of anomaly detector that computes some complicated statistic over all the previous components' internal features. And for good measure, this anomaly detector is often hard to differentiate over. Now, this in itself is okay. Maybe we actually need very complicated defenses to solve adversarial examples. But more often than not, the best attacks on these types of systems are actually fairly simple. And what I often see is an evaluation that sort of tries to attack the entire defense at once, usually by formulating some crazy loss function with a bunch of weighted terms. And there's just very little chance that this will work. But even when you have just 2 loss terms to deal with, you have to be a bit careful. And with more, we'll just get a very expensive attack to run. It'll probably fail, and we won't really know why. So what do we do? As with many computer systems, there's probably going to be a weakest link somewhere. And so for quite a few complex defenses that we looked at, we evaluated each of their components individually and found that many of them ultimately don't really matter and can just be ignored by the attack. And among the important components that are left, there's usually some that are very easy to attack and that can break the whole system. So a specific technique that we used in some of our attacks, and I'll talk about in a bit more detail, are so-called feature adversaries. And this is just a really simple and cool attack technique that I think more people should know about. So let's see an example for how to break a classifier that's augmented with some kind of anomaly detector. So we start with a normal picture of guacamole. The model will classify this correctly, and the anomaly detector will look at some internal features of the model and say that the input is okay. So now to build an adversarial example for our cat picture, we'll search for a perturbation that makes the model's entire internal features match those of the guacamole picture. And this is great because it hits 2 birds with 1 stone. Because the model's internal features now match those of the guacamole picture, the model will classify our attack as guacamole, and the anomaly detector will also consider the features as valid. So we've attacked the whole system without actually having to directly attack the anomaly detector, or even really having to understand how it works internally. It's just garbage in, garbage out. So the next point is more of a meta point, really. A feeling I get from some defense evaluations is that authors are mostly trying to convince the reviewers that their defense is robust, rather than being convinced about this themselves. And unfortunately, if we don't try to break our own defenses, someone else probably will later. One symptom of this are defense evaluations that evaluate a huge number of non-adaptive attacks, but only spend a tiny proportion of the evaluation on ideas that actually have a chance to work. And so you can think of it like this. If I was offered $1 million to break my own defense, what kind of attack would I build? Probably an adaptive one. So my ideal situation would be that defense evaluations in papers would be mainly about adaptive attacks. Showing that a defense resists non-adaptive attacks is kind of a formality at this point. It should definitely be in the paper, but it's not really the most important message. And when describing these adaptive attacks, we also shouldn't beat around the bush. So usually defenses rely on 1 or 2 very crucial assumptions or invariants, and so we should really just attack those directly with the strongest possible attack strategy we can think of. It's also nice to see some standard evaluation guidelines being followed routinely by authors that my co-authors actually wrote down last year. But this also shouldn't be taken as just a checklist to go through to appease reviewers. And on top of that, it's also worth noting that these guidelines also apply to adaptive attacks. So things like checking that an attack has converge properly, or that an attack succeeds when the perturbation budget is unbounded, these are things that should also hold for adaptive attacks, and so it's good to check these. And the particularly striking failure case that we see in some evaluations is that a proposed adaptive attack actually performs worse than the best non-adaptive attack. And this should, of course, never be the case if the adaptive attack was designed to be as strong as possible. Okay, so let me now take a step back and talk about a slightly broader problem that we have in this field. In the end, most defenses against adversarial examples are heuristic and need to be empirically evaluated. And we know that this is really hard. So there's always, unfortunately, a chance that even if we put in our best efforts to evaluate our defenses, someone else will later find a stronger attack. And ultimately, that's just the nature of empirical research in computer security. But the way that we react to these subsequent breaks currently looks a little like this. And to be specific, I recently reviewed about 40 defenses that I know of that have been broken by a subsequent paper over the past few years. Of these papers, I found one that was broken before being presented at a conference, and the authors retracted the paper. And I found another one where the authors amended the archive version with a footnote that acknowledges the subsequent attack. And the 38 other papers still present the original evaluation results as is. So why is this problematic? Mainly because it makes it much harder for people, especially newcomers, to navigate this field and to understand what has been tried and what works and what doesn't. And it's actually quite common to see new papers that reference and build on some earlier defense, even though that defense has actually been broken. And so what could we do better? So I'll use an example here from one of my own papers, which was published at iClear 2018. And this was my first paper on adversarial examples, and it proposed a heuristic defense against some black box attacks where the adversary doesn't have direct query access to the model. And I tried hard to break this defense, but apparently not hard enough, because there's been a line of work in the computer vision community that has found better attacks of this type sort of year after year. And despite this, the paper is still sometimes referenced as an effective defense in this model. And interestingly, I actually only learned about these attacks a couple months ago. So I'll just also note here that if you find an attack against the defense, it's a really good idea to contact the authors to let them know. So in the end, I amended the paper on archive to acknowledge these later attacks. It doesn't really matter much where to do this in the paper. It could be in the abstract, after the intro, in the results section. And it doesn't really need to invalidate the entire work either. This paper, for instance, had a bunch of other ideas and results that are still valid, and even the defense still seems to do a little bit better compared to undefended models, although not really as well as we would have hoped. But now at least the reader gets a very clear view of the status of the field, of what problems are still open, what ideas people have tried, and what worked and what didn't. So to conclude, the main takeaway from our work is that evaluating adversarial examples defenses is just hard. But there's still a lot of room for improvement in the way that we currently do this. And part of this is conceptual. Authors and reviewers have to realize that showing robustness against prior attacks is a fairly weak goal, and this is just not the way forward. And our conjecture here is actually that we're not going to come up with a fully universal attack, so defenses really have to be evaluated against adaptive attacks. And ideally, this would just be the bulk of a paper's evaluation section. My hope would be to read each evaluation section and be convinced that the authors really tried as hard as possible to break their own defense, but failed. And this also means that defense authors have to learn to build strong attacks. And there's no better way to do that than to practice. And I think our paper can really help here. And as you sort of break your teeth on a bunch of defenses, as we did, it'll also become easier and easier to come up with attacks that are both simpler and stronger. And by trying to attack other defenses, you'll also help to sort of have more independent reevaluations in the field, which will just be very beneficial. And finally, if a defense at some point gets broken, just acknowledge it, amend your paper, and just continue doing research towards solving this really hard and fascinating problem. If you have any question, please reach out to me. Thanks a lot.